Functional dependencies are a generalization of keys, and they play a major role in the theory of relational database design. On this slide we see again the table courses. Each course has a course number, a title, an instructor, and we store the phone number of the instructor. In this table, a functional dependency, short FD, is the instructor uniquely determines the phone number. And we write this using such an arrow that the instructor uniquely determines the phone number. Whenever we have two rows in the table that agree on the instructor name, then they must also agree on the phone number. In other words, you could say that the phone only depends on the instructor and not on the other columns in the table. In general, a functional dependency takes the following shape. On the left we have a set of attributes a1 up to an, then we have an arrow, and on the right we again have a set of attributes b1 up to bm. Usually we will not write the set brackets, so we will drop the set brackets, just writing a1 up to an, arrow b1 up to bm. This functional dependency holds for a relation R in database state I if the following condition holds, namely if we take two tuples from IR, so from the table associated to R in this database state I, then if we consider two tuples and these two tuples agree on all the values for the attributes A, so they agree on A1, A2 up to AN, then these two tuples must also agree on the values for B1, B2 up to Bm. So a functional dependency is like a partial key. It uniquely determines some of the attributes, namely in this case B1 up to Bm, but not all of them in general. And as we've already mentioned, we read this functional dependency as follows. We say that A1 up to n functionally or uniquely determine B1 up to Bm. So again, if we have two tuples that agree on the values for the attributes A, then they must also agree on the values for the attributes B. In general, a functional dependency has this shape. A1 up to an uniquely determine B1 up to Bm. So we have m attributes on the right. This is equivalent to stating m functional dependencies with a single attribute on the right. So here we're saying that A1 up to an uniquely determine the value of B1, and likewise they uniquely determine the value of B2, B3 up to Bm. So they determine all these values, which is equivalent to saying that B1 up to Bm are uniquely determined. So let's look at a simple example. Here we have a functional dependency with two attributes on the left and two on the right. A, B together uniquely determine the value of C and D. This is equivalent to saying that A and B together uniquely determine the value of C, and A and B together uniquely determine the value of D. But it's important to understand that this is not equivalent to saying that A uniquely determines the value of C and D, and B uniquely determines the value of C and D. Here, we have to know the values of A and B together. We have to know both values in order to know what the value of C and D is, whereas here we are saying that it's already enough to know the value of A in order to know what C and D are. And it's also enough to know the value of B in order to know what C and D are. This is not the same as the original statement, whereas this formulation is equivalent to the original statement. So since we can split our functional dependencies to make the right-hand sides into singular attributes, in the sequel it suffices to consider functional dependencies of the shape with a single attribute on the right. So let's make an in-depth comparison between keys and functional dependencies. First of all, it's important to understand that keys are functional dependencies. Let's say we are looking at a relation with attributes a1 up to n and b1 up to bm. Then a1 up to an is a key for this relation if and only if the functional dependency a1 up to an uniquely determine b1 up to bm holds. The key attributes uniquely determine the value of all other attributes. So if we have a functional dependency that involves all the attributes of the relation, then the left-hand side is a key. Let's have a look at a simple example. We have here our courses table, and the course number is a key of this table. So the course number uniquely determines all other attributes, namely the title, the instructor, and the phone. So we have a functional dependency, the course number uniquely determines title, instructor, and phone, and equivalently, remember that we can split functional dependencies on the right hand side, not on the left. We can split this on the right, and we get equivalently 3 functional dependencies saying that the course number uniquely determines the title, the course number uniquely determines the instructor, and the course number uniquely determines the phone number of the instructor. Functional dependencies are a generalization of keys. They are partial keys in the following sense. A functional dependency, a1 up to an, uniquely determines b1 up to bm, holds for a relation R if the set of attributes on the left, a1 up to n, is a key for the relation obtained by restricting R to the columns that appear in the functional dependency, so a1 up to n and b1 up to bm. So we're restricting the relation to the columns that actually appear in this functional dependency, and if then the left-hand side forms a key of this restricted relation, then this functional dependency holds for the original relation. For instance, if we take the table courses that we've seen before, and we restrict this to the instructor and the phone attribute, then we obtain this table, and in this restricted table, the instructor is a key. The instructor uniquely determines the row of this table. So in the original table courses, we have a function dependency, instructor uniquely determines phone. The goal of database normalization is to turn all functional dependencies into keys, because key constraints can be enforced by the database management system. So by turning functional dependencies into keys, the database management system can ensure all the functional dependencies. Just like keys, functional dependencies are constraints. They are not only intended for one database state, but they need to hold for all possible database states. For instance, in this example database state, the title of the course uniquely determines the course number. However, in general, this will not be true. So this is not true in all intended database states. As a designer of databases, we are only interested in those functional dependencies that hold for all intended database states. So let's practice a bit finding functional dependencies. We are only interested in those functional dependencies that hold in all intended database states. Here we have a table books, and this contains information about books and their authors. So we have attributes author, it's the name of the author, an attribute no, which is the number of the author, whether it's the first or the second author on the book. We have the title of the book, the publisher of the book, and the ISBN number, which identifies the book. So let's get started. What is uniquely determined by the ISBN? The ISBN uniquely determines the book, so it also uniquely determines the title of the book and the publisher. What about the author? Does the ISBN uniquely determine the author? In this table, we store different authors in different rows. So for instance, we have here two rows with the same ISBN, but a different author. So the ISBN does not uniquely determine the author. Does the author uniquely determine the title? In this database state, the name of the author indeed uniquely determines the title. However, this will in general not be true. We can have authors that write multiple books or authors with the same name that write different books and so on. So this functional dependency holds only for this database state, but we are not interested in it because we only want those functional dependencies that hold in general. What does the title determine? If I tell you the title of a book, what else can you tell me about the properties? It does not uniquely determine the author, also not number. We could have different books with the same name at different publishers. So the title in this database state, the title uniquely determines the publisher, but in general this will not be true. We could have two publishers that publish a book with the same title. So the title also does not uniquely determine the ISBN. So actually here the title does not determine any other attribute. What about the combination of ISBN and the number of the author on the book? So if I tell you the ISBN and I tell you I want the first or the second author, what can you tell? So we've already said the ISBN alone determines the title and the publisher. So ISBN number still determine title and publisher, but additionally, if you tell me also the number, then we also know what the author is. The ISBN uniquely identifies the book, and if you tell me that you want the first or the second author, then this will uniquely determine the name of the author. What about the combination of the ISBN and the author name? Does this uniquely determine the number? So whether this is the first or the second author? Again, in this database state, it uniquely determines the number of the author. If I tell you the ISBN and the name of the author, you can tell me whether this author is first, second, or third author. However, in general, this is questionable, because we could have books written by two authors with the same name. Clearly with the same last name this is not difficult, but even if we would include the first name, then still it's possible that we have two authors on a book that have the same first and last name, but are different people. So this functional dependency is questionable, and one should not take it up into the database design. What about the title, the publisher, and the number together? So the publisher of the book is known, the title is known, and the number of the author. Does this together determine the name of the author? Again, this is a functional dependency that is questionable because we could have fresh editions of the same book, so maybe the third, the fourth, the fifth edition, and this 5th edition maybe has the same title, but the author order may change. Maybe on the 3rd edition the 2nd author has contributed a lot and has become 1st author. So it's not clear that between different editions of the book, the author order has to stay the same. So also this functional dependency is questionable. And we should not take it up into our design of the database. During the database design, we should really only use those functional dependencies that are unquestionable. The database normalization changes the structure of our tables, the structure of our database schema, depending on the functional dependencies. If later on it turns out that we've used the wrong functional dependencies that do not hold in general, then this is something very difficult to correct later on, because it means that we have to change the structure of the tables, we have to delete tables, create new tables, and all this while trying to preserve the data that is stored in these tables. So it's really important to start the database design using the correct set of functional dependencies, only those functional dependencies that we are sure are completely unquestionable, that will hold for every intended database state. Let's have a look at this table and discuss what functional dependencies hold in general. We have a table with homework results. We have columns student ID, the first name, the last name of the student, the exercise number, the points that the student has obtained for this exercise, and the maximum number of points obtainable for this exercise. So which functional dependencies hold in general? Clearly, the student ID should uniquely identify the student. So the student ID should uniquely identify the first and the last name. It does not determine the exercise. It does not determine the number of points if there's multiple exercises. And it also does not determine the maximum number of points if there's multiple exercises. So the SID determines just the first and the last name. The exercise should also uniquely determine the maximum points that are obtainable for this exercise. So we have functional dependency from exercise to maximum number of points. And finally, if we have the combination of SID and the exercise, then we also know what the points are that the student has obtained. So the SID and the exercise together determine everything. The first, the last name, the points and the maximum points. So the SID and the exercise together form a key for this table. So let's also look what functional dependencies hold for this particular database state, so for the table shown on the screen, but they do not hold in general. If we're looking at our students, then we do not have students that have the same first and last name. Actually, we do not even have students that have the same first name here. The first name uniquely identifies the last name for this table. And the first name also uniquely identifies the SID. Especially if we take first and last name together, then also they uniquely identify the student ID. But this only holds in this table, this does not hold in general. In particular, if we would add a functional dependency that first and last name together uniquely identify the student, so give us uniquely the student ID, then taking such a functional dependency up in our modeling decisions would prevent the additions of students that have the same name. So we could never add two students with the same name to this table if we want to satisfy this functional dependency. So this is not a functional dependency that we should take up for our design.